So the first chromatography technique that we're going to learn about in a bit of detail is thin layer chromatography, which is called TLC for short. And in some ways it's closely related to the shirt chromatography that we've seen, or paper chromatography, because you have a stationary phase which works by adsorbing, sticking to molecules as they try to move across it. But in this case, instead of a shirt or a piece of paper, what you have is a plate. So this would be either a glass or a plastic sheet, and on one surface of it, it has a thin layer of the stationary phase. So it's a plate with a thin layer of adsorbent material. Adsorbent, remember, comes from the word adsorption, which is sticking on the surface. It's different from absorption, which is soaking into a material. Adsorption is just sticking on the surface of a material. So an adsorbent material is one which is good at getting other molecules to stick on its surface. So it's a plate with a thin layer of adsorbent material, and you can use various different substances, but the most commonly used one is SiO2, which is silica, which is just a highly purified form of quartz. And what you do is you grind it down into very fine particles, which are very uniform in size, so they're graded so that they have very uniform size and they're very uniformly spread over the surface. And that's what gives you the good resolution. The difference from, say, paper, where you have lots of fibres pointing in random directions with different lengths and thicknesses and so on, there you can see the scope is for different molecules to find routes which are harder or easier to move up depending on the particular fibres they encounter. And that's what causes the spots to spread out as they get, different molecules getting different experiences as they move up the piece of paper. But with this, because this material is so uniform, basically the molecules all get extremely similar experience as they move up, and therefore they move at much more similar rates, and the spots don't spread out as much. That's why this is a really important method, because it gives you much better resolution than paper can do. So that's your plate with a thin layer of adsorbent material, and that adsorbent material is going to be our stationary phase. Okay, so stationary phase, remember, means that it doesn't move. So its job is to stay fixed, and it's going to try to hold back the molecules that we're analysing as they try to move up the plate. So the stationary phase in chromatography, its job is always to provide a way of trying to hold back substances from moving. Okay, so what do we do with it? Well, what we do is we rule a starting line somewhere near the bottom. Okay, so that's going to be our starting line, which you just normally would rule a pencil line there. And onto that starting line, you put really tiny spots of the substance, of the mixtures that you're trying to analyse. Okay, so these are spots of the mixture to be analysed. And there's a lot of skill to this. So what you try to do is to get spots which are as tiny as possible, because obviously the less spread out they are in that direction, the better the resolution you're likely to be able to achieve when you run the chromatogram. So organic chemists spend time doing this very carefully, putting tiny spots on, letting them dry, then adding another little bit directly over the top, so that you build up enough substance but without allowing any significant spreading out. So that's ready now to roll once you've got your spots of mixture on there. So what you do is you put it in a container, and into the container you put a solvent. Okay, so this would be the solvent here at the bottom. Now the crucial thing, as you can see in the picture there, is that the solvent doesn't come up as high as where the spots are. Because if it did, the spots would just dissolve in the solvent and disappear into this load of liquid at the bottom. So it's very important when you draw this that you make sure that the solvent level comes below where the starting line is. And that means that the only way the solvent can get at the material in the spots is by rising up the plate. And it does that by capillary action, which means basically that it tends to stick to the surface of the particles a little bit, and it can sort of climb up between one particle and another, making use of these attractive forces that allow it to cling to the surface. So basically, by hook or by crook, the solvent rises up the plate. And as it passes these spots, the substances in the spots will tend to dissolve in the solvent to varying degrees. Different substances will have different solubilities, but they all have the chance, at least, to dissolve in the solvent as it passes. So, because the solvent is moving, and in at least some cases is going to get the substances in the mixture moving as well, it's called the mobile phase. Okay, and the job of the mobile phase is to move the substances being analysed across the stationary phase. It's important you put a lid on it. Okay, that's just a sort of practicality of it, because it wouldn't be too much of an issue if you're just using water because it's not very volatile, but organic solvents tend to be quite volatile, and if you didn't put a lid on it, what would tend to happen is that the solvent would evaporate before it got very far up the plate and the method wouldn't really work. But by putting a lid on, you saturate the vapour in here, and that allows the solvent to avoid that evaporation problem. So this is a lid to minimise evaporation of the solvent. Okay, so that's your basic setup. So the solvent rises up the plate, the materials in it dissolve to some extent and move with the solvent. So sometime later, the spots will no longer be on the starting line. Instead, they'll be somewhere up here. Now the solvent will gradually rise up, and what you'll tend to do is stop the experiment when the solvent gets up near the top. So the level the solvent has reached we call the solvent front. Okay, and you generally run the chromatogram until the solvent front is somewhere up near the top of the plate. And you can see it because it just looks wet on this part of the plate and dry up there, so it's very visually easy to see when the solvent has reached that point. So the crucial question is, well, what's happened to the spots? Well, if they contain mixtures, in general the mixtures will have had different mobilities, and we'll pick that apart in a bit more detail in a minute. But in general, if you had a mixture of 3 components, then with a bit of luck what you'd find is that one of them might have had quite limited mobility, so it would still somewhere be down near the bottom. One would have had a bit more, and one might have had quite high mobility. So you might get 3 spots like that. Now, of course, you might not be that lucky. If the substances just happen to have very similar mobilities, they might not be separated. So you can never look at that and say, right, 3 spots means 3 substances. What you can say is 3 spots means at least 3 substances. But there could be more, because there could be more than one substance contributing to any one of those spots. So that's the principle of the method. What we need to do now is, first of all, to understand in a bit more detail how this separation actually occurs and what it depends on. Now, we can actually quantify these differences in mobility of different substances, and that's something you need to know about. So here's our starting position. Remember, so we've got the starting line here, and we've got our mixture loaded as a tightly focused spot on the starting line, and then we dip it in some solvent and we allow the solvent to rise up the plate. So sometime later the spot will have moved and the solvent will have reached up there, and remember we call that the solvent front. And you can see that because that's how far the plate looks wet and it's still dry up there. And the substances in the spot will hopefully have separated out. So instead of having a spot down there, we might hopefully say have one here and one there, or whatever you've got in your mixture. So the way we quantify the mobility of each of these individual substances is by defining something called RF. And RF stands for retention factor, or sometimes retardation factor, but you don't have to use those long names, you can just call it RF. And so what you measure is, first of all, the distance from the starting line to the spot that you're interested in, and specifically, because obviously it has a finite size, you're supposed to do it to the middle of the spot. So it's going to go basically to there, and you measure that distance, and it doesn't matter what units you're going to measure it in, because as you'll see in a minute, we're going to take a ratio of distances, so you can measure them in any units. So normally you probably measure millimeters, or they will often, if they give you these in exams, they'll put it on squared paper, so you can just count the squares. So that's the distance moved by the substance, and you also measure this distance, which is the distance moved by the solvent. So RF is that ratio. It's simply the distance moved by the substance you're interested in divided by the distance moved by the solvent. And that number stays constant as the solvent is moving up the plate. So if you stopped the experiment earlier, the solvent would only have got to there, but obviously the substance would also have only travelled a smaller distance. And if you calculated the ratio, you'd find it would be the same number. So that stays constant as the migration happens. And you can see that RF is going to be a number between 0 and 1. So if you have a substance which adsorbs incredibly strongly to the stationary phase and therefore doesn't really move at all when the solvent progresses up there, the distance moved by the substance is 0, and 0 divided by anything is 0. So that would have a retention factor of 0. On the other hand, if you have a substance which is very soluble in the solvent and is easily dragged away from the stationary phase, then it will go all the way up there with the solvent front, and those two distances will be the same, so the retention factor will be 1. So this RF will always be a number between 0 and 1, and the bigger the number, the more easily it moves. In other words, the weaker the retention. So the bigger the number, the poorer the adsorption to the stationary phase is how you would interpret it. Now, because the RF value, the mobility of the substance on the chromatogram, depends on this balance between two things, strength of adsorption and the solubility in the solvent, it's quite difficult to predict what the mobility of any substance would be, or even what the relative mobility of substances would be, because you have to, think about what's the difference in the strength of adsorption as well as what's the difference in the solubility, and that can usually be a very difficult thing to do. So that's not something they're going to generally ask you to do at A level. So they're not just going to show you two spots like that and say, right, here are two substances, so say one of them is this and one of them is this. They're not going to say, right, which spot is which, because that's too difficult a question. But what they might do is ask you something which still tests your understanding of the physical process of what's going on. So they'll say, right, okay, as it happens, this substance is the top spot and this substance is the bottom spot. Okay, so they'll give you that information, and then they'll say, suppose you used a more polar solvent. So your stationary phase might have been, say, chlorobutane or something. That was solvent 1. And then they say, suppose you repeat the experiment, but this time you have a more polar solvent, like, say, ethanoic acid, for example. What difference would that make to the relative mobilities? So what you think is, well, if the solvent's more polar, then polar substances are going to increase their solubility in it. Because remember, polar substances don't dissolve well in non-polar things because they can't form those favourable permanent dipole-dipole interactions or hydrogen bonds with non-polar solvents. If you increase the polarity of the solvent, you increase the ability to form those favourable polar interactions, and so you'll increase the solubility. So what you would expect is that with this solvent, which is more polar, then this one will move faster. And this one, well, you can't tell whether it would move faster or slower, but certainly you would expect the difference to be less. So, you know, it might even move slower, because it might be that the polar solvent is less good at dissolving a non-polar material. So you can't be sure it would go like that, but what you can say is that increasing the polarity of the solvent would increase the RF because it's more soluble in a more polar solvent. For that one. And for this one, there would be likely to be a decrease in RF because it's a non-polar substance, so it's going to be less soluble in a more polar solvent. So you've got to be able to think at that sort of level. What would changing the solvent do to the mobility of a particular substance? They might ask you the same kind of thing about the stationary phase in principle. They'd say, well, what if you make the stationary phase more polar? And again, you'd say, well, polar substances will then stick to it more strongly, so it'll be harder to get them moving, so their RF values will decrease, and so on. So that's the kind of level of interpretation that you need to be able to come up with. One of the things that TLC is very much used for in organic chemistry labs is following the progress of a reaction. Because it's quite a quick and cheap method, it's very popular as just a way of telling how far you've got in a reaction. So suppose, for example, you were doing this, oxidizing a primary alcohol, first to an aldehyde and then to a carboxylic acid. And we've always said that this first oxidation happens quite rapidly and then this happens more slowly, so you have to leave it for a long time, you know, reflux and all that kind of thing. But the question is, well, how long does that mean? Does it mean, you know, reflux for 5 minutes or 25 minutes or 6 days? You know, you need to know if you're going to use this as a method. And TLC can tell you. So let's imagine that we compare the mobility in TLC of a series of samples. So this could be the sample taken at the start of the reaction. Okay, so we haven't had time to form any product yet. So all we're going to see at the start of the reaction is one spot, which is going to be due to that substance. Okay, so here's our one spot here. And we know, because it's at the start of the reaction, that that's going to be that substance. And what we're going to expect is that when we take samples from the mixture later on in the reaction, that the amount of that will decrease, and that corresponds to this spot becoming smaller. So although that's quite a difficult thing to quantify, in a qualitative way you can see how the amount of a substance dwindles just by how the spot gets smaller. So sometime later, let's say this is the sample taken after 5 minutes. So it's been reacting in a pot, and then you take a little sample out after 5 minutes. Then what you're going to expect is that you'll still have some reaction, some reactant there, because we haven't left it for long enough for it all to be used up yet. But the spot's got smaller, because some of it has been converted into the aldehyde. So we should also expect to see another spot. And that other spot could come anywhere here, so let's put it, let's put it here, just for the hell of it, because we have no idea where it'll be, so it may as well be there. And so you can deduce that that is likely to be due to this substance. But we'll confirm that in a minute, so we'll just keep an open mind for the moment and say, right, well, another substance has appeared after 5 minutes. So now let's take a third lane, where this might be a sample taken after, let's say, 15 minutes. Okay, so we've let it react a lot longer now. And what you might find is that all of this has now reacted. So this spot along that line there will just have disappeared. Nothing at all there anymore, because all of the reactant has gone. But we'll now have lots of this. So this spot will have got bigger. But maybe we've got a hint of something else. And again, it could be lower down, it could be higher up, we don't know, but there's something else appearing. So that seems to make sense. It suggests that we've used up all of the reactant, we've formed more of something, a product, but we've also started to form a different product, which is up there. And then let's do a final one. So this might be a sample taken after, say, 30 minutes or 1 hour, let's say 1 hour. Okay, and now what you find is that you've got loads of this material and maybe none of this, or at least only a very small amount. So that would be consistent with this story, because it would say, right, if we take a sample at the beginning, no time for any of these to be formed, so what we see is that one, so that's what that spot is. After 5 minutes there's been some reaction, so there's less of this, so the spot's got smaller, and there's some of this, which is that new spot. So we can now pretty confidently say that this spot, which comes along this line here, is due to the aldehyde. Okay, so after 5 minutes we've got some aldehyde, but we've still got some unreacted alcohol. So we leave it for a bit longer, and by the time we reach 15 minutes, basically all of that has gone. So we don't see that spot anymore along that line where it comes, but we've got a nice big healthy aldehyde spot. However, there's a sign of something new starting to appear as well. And when we leave it for longer, basically the aldehyde that we've built up there all but disappears again, and now it's got converted into this new material up there. And so that fits with this spot being the carboxylic acid that's formed in the end. Okay, so this is the benzoic acid. So you can see how TLC is very useful for that. Its great advantages are, as I say, that it's quick to do, so you can, it depends on what sort of resolution you're aiming at, but you can often get separation like that in, a sort of 5 minute process of just allowing the solvent to run up the thing. And it's cheap, because TLC plates don't cost very much, they're disposable items. But the disadvantage, the limitation of it, is that often spots are not resolved, so I've drawn those as if they're nice and clearly separate from one another. But it wouldn't be a big surprise if you sort of got a smear like this and you think, well, that looks like two spots merging into one another, but then obviously the closer they become, the harder it becomes to separate them and tell what's going on. Well, when that happens, what you normally do is you switch to a different solvent, because it may be that in one solvent two substances have very similar mobility, but if you change the solvent they may then have very different mobilities. So there are ways of improving it. But the thing to do is just practice lots of examples, and TLC is a relatively simple method then to get your head around.